Hello, here's another oscillations question. We've got a simple pendulum this time. So this is our figure over here with a simple pendulum, a sphere suspended from a light string from a rigid support. Yep. Displaced 50 millimeters from its vertical equilibrium position and released at time t equals 0. So this is the graph that we've got here. So they've taken negative off to the left. This is our displacement against time, noting that we've got millimeters here. So use this graph to determine the frequency of oscillation of the pendulum. Right, this will be fun with these squares on here. So we're starting at, we've got one minimum here, so we need to go to the next minimum. So that's this line coming up here, that's there. So that's the bit we're looking for. That's at 2, that's at 3. So we're not quite at halfway. That is halfway. So that must be 2.4 seconds is our period. So here we've got t is 2.4. So the frequency is 1 over that. So our frequency 1 over 2.4 is 0.42 hertz. That's fine. Use figure 3.2 or otherwise, well, I don't think we'll otherwise it, to determine the maximum speed of the sphere. Right, Vmax is equal to a omega, which is equal to a times 2 pi f. Right, we've got f. A is whatever this is up here. So yeah, that's 1, 2, 3, 4, 5. So yeah, that's 50 millimeters. So we just need to make sure we've got all the right bits in all of this. So we've got 50 millimeters times 2 times pi times f. So that's 100 times 1 over 1,000. So that's a tenth of 2 pi f. Right, let's just type all of that in. And we've got, it's going to be, well, I mean, we can see, well, I've typed it in anyway. So it's 0.13 meters per second. But that fits because we're going to have 0.042 by multiplied by 3 and a bit. So yeah, that comes out at 0.13 is a bit of a sanity check on that. So again, standard simple harmonic motion stuff here of these sort of formulae that you'll get used to once you've done more and more of these questions. Right, the sphere is now released from rest with a displacement of 25 millimeters. They've dropped it down to half the maximum displacement, half the amplitude. State with a reason the change, if any, in the frequency of the oscillations. Right, so frequency is unchanged because in SHM, in simple harmonic motion, frequency or period independent of amplitude. Yeah, we showed that in one of the earlier videos. You know, we know that our time period for a simple pendulum, 2 pi root L over G, it only depends upon the length of the pendulum and the acceleration due to gravity, providing we're at small angle. It has nothing to do with our displacement or our amplitude. So that will stay unchanged. The maximum kinetic energy of the sphere, well, we know that well, kinetic energy is proportional to v squared, and v is proportional to a. In this case, our v max is proportional to the amplitude. Oh, excuse me, got the hiccups. So kinetic energy is going to be proportional to a squared. So if we've halved the amplitude, then we've reduced the kinetic energy is down by a quarter. So you'll be able to turn that into a couple of sentences there for explaining the changes in maximum kinetic energy. So that's Ke max down by a quarter. So yeah, all straightforward stuff. Right, in turbulent air for part C, the wingtip of an aircraft can vibrate vertically. Right, so we're on something completely different now. We've had enough of pendulums. To investigate this effect, the acceleration and the vertical displacement of the wingtip are measured, and they're shown in this graph here. Explain how figure 3.3 suggests that the wingtip undergoes simple harmonic motion under test conditions. Right, so for simple harmonic motion, and we want to have two things. We want to have that the acceleration is proportional to the displacement. So that's one thing. So we've got that because there's a straight line. And then we also want to have that the negative gradient is the next thing we'll be looking at. The negative gradient shows that the acceleration is in the opposite direction to the displacement, opposite direction to displacement. And you might even want to put in something like i.e. The acceleration acts towards the equilibrium point. So just to have everything in there, because then you've mentioned all of the key things. You've mentioned two things about the graph, that you've got a straight line, you've got a negative gradient. You've mentioned two things about simple harmonic motion, acceleration being proportional to displacement and it being in the opposite direction. And then you just added in this kicker of a bit of terminology with acting towards the equilibrium point. Right, use figure 3.3 to determine the frequency of the vibration. Right, so the gradient is equal to omega squared, which is equal to 4 pi squared f squared. So let's get the gradient and then we can just work all of this stuff out. So the gradient is really hard to read off of here because I've had to make it so small to fit on the page, but it looks like we're going through this point here, which is at -4.5, and again this is in millimeters. Well, you can either just take it going through the origin or come out the other side. We're going to end up getting the same thing because we know they've drawn a straight line on here. So we can say that the gradient or the magnitude of the gradient is omega squared, because we've got to take that negative bit out of it. We don't care that there's a minus sign there. So we've got 5/4 on that for our gradient. So and that's got a 10 to the -3 on the denominator. So we're going to have 5/4 times 10 to the 3 is equal to 2 pi f all squared. So square root the left hand, well, square root both sides and divide by 2 pi, and that will give us what f is. And I've been typing that in while I've been talking about it. It comes out at 5.6, 3 hertz. I think we're going to be pushing it to go to 3 significant figures. What we got in the question, these have all been 2 sig fig. 2 here, yeah, everything's 2, so let's leave the 3 out and say we got 5.6 hertz. So yeah, standard stuff. Again, these are just drill questions to make sure that you're slick on everything that's kicking off in SHM.